Hello, and um, welcome back to AMRCOG online sessions. This is Dr. Gubara, and today I will talk about some basic concepts in biostatistics. Just a notice before we start that this lecture targets students with very little experience in biostatistics, okay? There might be some simplified examples, definitions, interpretations that's not perfectly accurate in the academic context. So today, what we're going to do today is just to scratch the surface, yeah? I like to start with the hypothesis testing, the concept of the null hypothesis and the alternative hypothesis, because first there's a question. You can take your time to read it, and at the end of this lecture today, we will solve this question. Hope you can solve it by yourself. And it's very easy. It comes out in the exam. And the idea of the null and the alternative hypothesis, I'd like to start with because there are so many misconceptions. Some people think our statistical test, the null and the alternative hypothesis with the chi-square and t-test and the ANOVA and correlation, and they are all different things. Yeah, and they're not equations, and they're not something you can do by your hand. Things you choose between. You're not going to say, I will choose to do the null hypothesis this time, but next time I will choose the alternative hypothesis. No. This is not what we're talking about. This has nothing to do with the null hypothesis and the alternative hypothesis. And they're not the aim of the work. They're not just one hypothesis for the whole paper research. I want to say that they're philosophical concepts, basic concepts. They're hidden within the statistical test themselves. So every statistical test that you heard about, the t-test, the chi-square, the correlation, the regression, every test has the null hypothesis and alternative hypothesis. Today we do have Nina and Alex. They're gonna, help us to understand this concept today. So let's take an example first. If I show you two different cars, yeah, and you're thinking which one you should go for. So let's just first take the opinion from the people, from our friends, Nina and Alex. Nina will tell you that they're similar. There's no difference, no difference. The difference is null. Well, Alex will tell you that no, they're different, the same thing. So one of the cars is better than the other one, and we don't know which one's better than the other one, but we will figure that later. But as for that moment, I want to tell you that they are different. This is Alex. Nina would say, no. Okay, so which one should we believe? Should we believe Nina? Should we believe Alex? I think we should test their theory first. We should test their words. We should test their saying first. You will request a test drive. Yeah, you need to test the car yourself. Suppose that this time the both cars have the same speed. There's no noticeable difference. No noticeable difference at all. At all. They are the same thing. So, okay, Nina, you're right this time. They're similar. No difference. No difference between both cars. So I'm sorry, Alex, this time you were wrong. No, they're not different, Alex. No. Nina was right this time. Suppose, in another context, you drove the cars and you figure out that, no, they're different speed. And the difference is really noticeable. Okay? The difference is really noticeable this time. Then you will reject what Nina said because they're different. You can notice the difference between the speed of both cars. And this time, Alex was right. Yeah, they are different. I hope you noticed that every time we start with Nina and Alex comes as a sequel. And this is important for you to know. I'll explain that in a minute later on this lecture, but just bear that in mind for the moment, okay? That we, every time we start with the null hypothesis, this is our concern. We start with Nina first, Alex comes as a sequelae. And as you saw, they can't be the same thing. We can't accept both. We can't reject both. If we reject the null, we will then accept the alternative, and if we accept the null, we reject the alternative. It comes like that. It goes like that. This is the way it works. Back to real life. Let's take a real example from real life. Suppose that you want to find the difference or relation between HPV infection and cervical cancer. Before you do any statistical analysis, before you even think about it, before you do the equations, before you know for sure that there are two end results. You don't know anything about HPV and you don't know anything about cervical cancer. Suppose this is the first encounter for you. You know nothing about it. Okay? So there are two possibilities. Either the HPV has, impacts on the rate of cervical cancer, or HPV has nothing to do with the cervical cancer. So based on that, you write down your theory. I mean, you don't need to write that down in the paper. So this is just basics in your mind that the null hypothesis, with that symbol H0, as you can see on the left-hand side, no relation between HPV and cervical cancer. Okay, and H1, there is a relation between HPV and cervical cancer. This is the alternative hypothesis. That those two lines are hidden within every statistical test you'll carry. Okay. So now what? A hypothesis needs a test, just like we did in the test drive, yeah? We need to test whether the women with HPV infection have similar rates of cervical cancer to those without HPV infection, yeah? So let us imagine that rate of cervical cancer in women with HPV this time significantly higher than those without infection. Okay, so we are trying to say that both groups are different, right? Yeah, so that's correct. Good. So we will reject because they're different. We will say that Nina, you were wrong this time, and we will reject what we said. So this time we will reject the null hypothesis, and intuitively, as a sequelae, we will accept what Alex said. We will accept the alternative hypothesis. That's the way it works. Okay, so it's all about the null hypothesis to be accepted or rejected. So we start with Nina, then Alex will come as a sequel. The alternative hypothesis will come the opposite to the null hypothesis intuitively. This is pretty much like when you're solving the SPA questions. The correct answer is number A, for example, then the responses A, B, C, D must be wrong. But you don't do that in the exam. You just check on the correct answer. You don't need to, cross or strike off the other answers. You just, click on the correct answer and that's it. And intuitively, all other answers, are marked wrong, for your response. Okay, so all you need to do is to have a clear idea about the null hypothesis, and then the test. Then to test the null hypothesis. Okay, to show whether it is right or wrong. Simple as that. Every test we heard about. So now we talk about the test. Every test we heard about, we used or studied, is designed to test the null hypothesis. Okay, the t-test, the chi-square test, the ANOVA, the correlation. All these tests, all these statistical methods are called test, so-called test, because they test the validity of the null hypothesis. The tests are going to tell you whether to accept or reject the null hypothesis. That's in plain English. So for the null and Sorry about that noise. Okay, for the null and the alternative hypothesis, how the test is gonna, at the end of the day, the test will tell you whether to accept or reject the null hypothesis using the p-value. I think we've all heard about the p-value law, but we just need to know today, we need today to have a clear concept about the p-value, what the p-value is, okay? P-value is the percentage of a chance. It's an acronym for the probability value. So P for the probability. So what is it all about? It's all about the percentage that the difference you notice is due to nothing but chance. Just a chance, just a luck. The percentage of the difference you notice is not a real difference. It was just a matter of luck. It was just a matter of luck. Back to the cars example. In the cars example, is the percentage that the difference you noticed wasn't because one car was better than the other one. No, it was just because bad weather, for example, bad driver, or any other bad luck or chance. It is a false difference. What is the probability of that difference was false, was fake? That's the p-value. So this is what you need to do in the exam. You need to do the interpretation of the p-value. You just don't treat it like that. If you don't have a clear concept, if you don't have a clear concept about the p-value, you need to do a little bit of interpretation to make it easier for yourself to understand. So every time you see the p-value in the exam, strike it off. Just strike it off in your mind and put that instead. The probability of false difference. So remove the p-value and put that sentence, the probability of false difference. Like if I told you that the p-value for t-test was 0.01. Every test, as I might have said to you, every test in the statistics does have a p-value. It will bring the p-value at the end of the day. So suppose that the t-test told you that the p-value of the t-test was 0.01. I will come to the concept of the t-test and chi-squared and the type statistical test later on, but today we just need to focus on the idea and the concept of the null hypothesis and statistical errors, okay? So the p-value for t-test was 0.01, which basically means 1%. So the probability of false difference is 1%. That's what I need you to put that in instead. Strike the p-value, strike it off, and put the sentence of the probability of false difference is 1%. Okay, another example, the p-value for chi-squared test, this time the chi-squared test was 0.005. Okay, that means that the probability of a false difference is 5 in 1,000. 5 in 1,000. There's the 5 in 1,000 probability that what you saw today, what you noticed in the difference today was just because of chance, just because of luck. 5 in 1,000. I'm talking about the value and the value and the value because we need to put a cutoff. How this p-value will tell me either to accept or reject the null hypothesis. We need to set a cutoff in the p-value, and this cutoff, the 5% that we all know about, we will accept the null hypothesis only if the probability of a false difference is 5% or more. We're gonna say this probability of a chance, this probability of fake or false difference or fake difference is too high to accept. It's too high actually to think that this difference was real. That probability is, that difference is, that cutoff is 5%. If we have 6%, 7%, 10% chance that that difference you saw in the car and that car and the other car was just due to luck, just due to chance, just due to weather, just due to any other factors other than that one car was greater, better than the other one. Okay, if that chance, that probability is more than 5%, we will accept the null hypothesis. We'll assume that really both cars are the same, and what we saw today was merely due to luck, is merely due to chance. Okay. At that point, we will accept the null hypothesis, and as a sequelae, we will reject the alternative hypothesis. Okay. So back to real life example. If we found that the rate of cervical cancer in women with HPV was 70%, 70%, while in women without HPV infection was 20%, 20%, so 70 to 20. This is, as you can see, this is obvious, isn't it? Yeah, this is an obvious difference. But the chi-square test produced p-value of 10%. So I'm trying to say that there is a 10% probability that this difference you noticed in your research, you reported in your research, or you reported from the chi-square test, that 70 to 20 was utterly due to luck. It was just due to luck. Maybe some different, maybe you picked up the wrong groups, maybe you picked up some older women or younger women, maybe you have a fault in the sample size, maybe you have a fault, maybe you did something that's not correct, maybe. But that difference, as we can interpret the p-value, it's more than 5%, it's 10%. So this 10% fake probability of fake difference, this is too much to accept. So we will assume that both groups are the same. Yeah, we assume that both groups are the same, and based on that case, we will accept the null hypothesis, and as a consecutive way, we will reject the alternative hypothesis, and we will report that both groups are actually the same thing, because the p-value is more than 5%, it is 10%. Suppose that some point later on, we found that, same example, exactly the same example, but this time the p-value is 4%. So this means that there's a 4% probability that this difference, 70% to 20%, was utterly due to luck. Well, 4% isn't much, yeah? It's less than the 5% cutoff, yeah? So it's a small probability. It's little probability. It's less than 5% probability that this is a fake difference. As I might have told you, earlier, that every statistical test, there's no zero p-value. There's nothing, there's no such thing. The p-value, you have to get a number from the p-value, okay? So every test, there'll be a p-value. The p-value means there's, at any point in your research, there's still a chance that you saw is a fake result, but you need to, which one to go? Yeah, I know there's some probability that you saw is a fake, is not real difference. But as long as it is less than 5%, you're okay with that. If it crossed 5%, is more than 5%, no, you're not okay with that. You not accept, you'll think that they are the same and there's no real difference. But it's less than 5%, okay, now we need to talk. Yeah, we do have a story here, yeah, isn't it? Do we? We do have something actually to report, yeah? Less than 5%, meaning that there's, very little probability of fake results. That means that we do have very high chances of real difference. So we will do what with the null? We will reject. Yeah, we will reject the null hypothesis this time. And alternatively, we will accept the alternative hypothesis. The idea of that null and null hypothesis and the alternative hypothesis, they're hidden. So as I might have told you, you never think about it when you do research, you never think about it when you do the statistical test. As I told you in the beginning of that lecture, that they're not equations, they're just the basic concepts. Well, these concepts we do need to swim up to the surface and become shiny. Yeah, when we bring in the idea of statistical errors. What are the errors? The first, before we define the error, we need to define what is right, right? Yeah. So if you accept something true, you did the right thing. Similarly, if we reject a false hypothesis, then you did the right thing. So accepting a true hypothesis is right, rejecting a false hypothesis is also right. Yet, accepting a false hypothesis, you did the wrong thing, you did something incorrect because you accepted a false thing. And similarly, you rejected true hypothesis, again, that was wrong. So we all know now that how to accept and how to reject a hypothesis based on the p-value. Who's going to tell me that the hypothesis is true or false? We don't know this yet, do we? We don't. No, we don't. We don't know this yet. We know now that we want to accept or we want to reject. Okay? But who's going to tell us if that hypothesis, the null hypothesis, is true or false? I tell you. Back to the HPV example, you discovered that 70% of women with HPV infection had cervical cancer. Yeah, but only, well, 20% of those without infection had cervical cancer. Yeah, well, the p-value of the chi-square test was 0.1, means 10%. Is 10% chance of false difference. Based on that, I'm just repeating what we said, a couple of minutes ago. You choose to accept the null hypothesis, and you're saying that HPV infection has nothing to do at all with the rate of cervical cancer. Yeah, based on the p-value, 10% is too much higher than the 5%, almost the double. But that's the problem. Yeah, I think we'll agree that there's a mistake here. Yeah, because we all know that. We all know about that we can't be right at all. Yeah. From the international databases, from the literature, from we study in the medical school, from the national statistics, from much published studies, we all know that HPV is associated with the cervical cancer. Yeah, there's a significant difference between HPV and non-HPV. So, from much more powerful studies, the null hypothesis cannot be true this time. But we accepted the null hypothesis because of the p-value. So it means that we've made a mistake. That mistake we call a statistical error because we accepted the null hypothesis and that was wrong. This brings us to the types of statistical errors. We have two types, type 1, type 2. Sometimes type 1 is referred as type A. Sometimes type 2 is referred as type B. We need to study those errors very carefully. And I'm going to start with the type 2 error. Why type 2? Because type 2 is the bigger number, 2. 2 is much more important. Think of it like a mnemonic. Which one is more dangerous? The both are errors, but there is an error and there's a blunder. Yeah, which one is a blunder? Which one is much more dangerous, much more important? Which one is much more that we need to have a big concern on it? Type 2. 2 is a bigger number. So 2 is a bigger mistake. Yeah, 2. So it's important. So we will start with type 2 first. Okay. Type 2 means a false negative. A false negative result. You accepted a false null hypothesis. Null hypothesis will tell you that they're both negative results. No, nothing there. That both groups are the same. Yeah. And that was false. But we accepted the false thing. That's type 2 error. Just like we did in the HPV example, as you remember, we accepted the false null and we assumed that the women with HPV are no different than women without HPV. You know what you did? You just get the patient. Because if you, if you implement this research into your clinical practice, you will, every time you have a woman with HPV infection, you tell her, now that's okay. We know from my research, I did research, and the research tells me that HPV infection has nothing to do at all with cervical cancer. And now you can go back home and, have a peace of mind. You just get the patient. This is why type 2 is much more important to study, much more important to, pay more attention on it than type 1. So type 2 is a false negative. You were able to find a difference between both groups. Like if I show you a criminal man, yeah, I told you this man is a criminal, and there's no evidence of that, or you failed to recognize that man was a criminal, and you release that man, you release into the society, and this man, what he's going to do? He's going to kill people. He's going to steal from people. He's going to sabotage, institutions or so, because that was then that's a big harm, isn't it? Yeah, that's a big harm. That's a big mistake. That's type 2 error. That's a false negative. Okay, now what about the other type? Type 1. Suppose that's a completely different example. You're doing research on the effect of hypertension on endometrial cancer. So hypertension, in particular, suppose that you have 100 patients with endometrial cancer with hypertension. You have 100 patients without hypertension, normotensive. And you follow up the patients for like 10 years or so, and at the end of the 10 years, how many patients do we have in the first arm, in the first group with the hypertension? Like 40 patients. So 40% of women with hypertension had endometrial cancer, and the other group without hypertension were just 10%. Okay, so the p-value, you did the chi-square test, and the p-value of the chi-square test was 1. Did you know this should be 1 in 1,000, not 1 in 10,000? That was a mistake. Sorry about that. So fix that. It's on, but it was just 1 in 1,000. So it means that, okay, since we have a p-value much less than the 5%, so we assume that there's a real difference here. It means that the hypertension here really makes a difference between both groups, yeah? And based on that, I would assume that no, they're not the same thing. No, Nina, you're wrong this time. I'll reject what you said. I'll reject the null hypothesis and accept the alternative hypothesis this time. And we all know that hypertension has nothing to do with the endometrial cancer. I made a mistake. We know this from the literature, from databases, from multiple published studies that tell us that null hypothesis should be true. Yeah, null hypothesis this time that we rejected. Nina was right, but I rejected Nina. I was wrong. I did a mistake. I should have, accepted what Nina said. I should have accepted the null hypothesis because from the databases, from the literature, from mobile studies, we all know that null hypertension are the same thing to endometrial cancer. Hypertension has nothing to do with endometrial cancer. So obviously you made a mistake, but this time you rejected a true null hypothesis. So type 1 or type A error is a false positive. When you reject true null hypothesis, you made a false positive, you made a type 1 error. So this is what you need to know about the type 1 and type 2, and this is like a recap slide. Type 1 is the false positive, type 2 is the false negative. You need to memorize this by heart because this table, comes in the exam frequently. You need to have a clear idea about the null, the alternative hypothesis, the false positive, false negative. Type 1 is less dangerous. It's almost type 2 is more dangerous. Type 2 can kill the patient, can make great harm to the patient. But type 1 is still an error, still can make harm, but less dangerous than type 2, less dangerous than type 2. Okay, type 2, you can miss a case of cancer like what we did in HPV example. Type 1, well, put the patient into stress, put the patient in anxiety for undue investigations, unnecessary investigations, unnecessary surgery, unnecessary intervention, but you're not going to kill the patient, yeah? You're not going to kill the patient. You don't kill the patient with type 1. Type 2 can make you miss a case of cancer. If you did that, that's a big harm. So type 2, the bigger number with the bigger mistake. back to the question that we, started with. So what do you think about the answer now of that question? The answer will be 3, 2, 1. That's the answer. I hope you enjoyed my lecture today, and I will, continue with you the biostatistics for the MRCOG. And thank you so much for listening. All the best luck. Thank you. Bye-bye.